need to do the level.
All right. Say we're given a better initial condition. Say we're given an initial condition that y of 1 equals -1. Let's do this in another color. Okay. So if y of 1 equals -1, that's this point right here. And we can imagine that at that instant, we know that, well, at 1, 1, we know that it has, when 1, -1, when x is 1 and y is -1, it has a slope of 3, the slope of the tangent line. So it's growing pretty rapidly, but then it's got to follow these guys. So the curve might look something like that. Okay? So it gives you a way to visualize what the curve would look like. Okay? The whole field taken together represents the general solution at any point x, y. As soon as you're given an initial condition, that tells you at that point where the curve must be going, and then you can judge by those sort of guideposts. Those little slope segments represent guideposts for the direction of the curve. Okay, now this is where I wanted to show you the technology, which the security settings aren't allowing me to do. Okay. But there's a lot of ways to do it. Now this is there's a link to this. If you guys are more tech savvy, I can't get the security settings on this to allow this. I've tried to allow add-ons and all that, update on it. What's that? Wolfram Alpha, I've never played with it there, but you could probably do it. Yeah. DField is another free one. It just requires Java. So you gotta be running Java. You can update it. You can install it for free or whatever.
What does the error say?
Security settings have blocked it, and I've turned down the security settings, and I've also enabled this as an add-on, the Java, and it's still not doing it. So
I think that means that I had that problem with that with another program, and it meant that it was an old version of Java that's not supported anymore.
right,
I had to actually
update Java.
No, I had to go back to Java and use an old version for a work thing that I had to do.
Yeah, and the other thing with these computers, they all have like deep freeze software on them, so anything that you install is gone the next day. So it sucks. All right, now here's something. There's also, you can do it on Maple. Maybe we'll do it there. I'll show you the commands. This is something I found. This is actually an Excel program that somebody created. Okay. Now that's not the one we're looking at. We're looking at a different equation. But I've also posted this. It's in technology demos or overhead demos.
What were you using 2 terms ago? Was it graph? You did the same.
Oh, it was DField.
It was DField.
Yeah, I'll have to talk to
But for some reason we can't get.
I'll talk to the tech guys and see if I can get them to enable this and have the updated software installed on it permanently. Because if I put it on, if I install it at the beginning of class, it's gone the next day. So they got to do it
I
permanently.
think that's what you were doing before, right? You installing Java every time.
Yeah, I installed Java before every class.
Yeah.
Okay, so we had x minus 2y. Here's dy dx, and it allows you to just put in x minus 2 times y. Just to be safe, I was using the times key. So a little asterisk. Okay, and we generated it from -2 to 2. But just to be safe, I'm going to go from -3 to 3 in both directions. -3 to 3. Enter. And calculate direction field. It's interesting. Somebody wrote this program, so it takes a while to do, but
Is it using Euler's method to plot the line?
it might be, or some other one. There's some other numerical.
Sure. But they just entered it. It's not like there's a command built in.
There's not a differential equation library in Excel.
Sure.
Somebody did this. And I'm not going to mess around with it. I don't care how it works. Just it works.
That was teacher.
It's like a really old video game.
Yeah. Math Blaster. Yeah.
It's like that.
That must have been 1982 or 83. I remember going into the computer lab, we were new, and playing Math Blaster.
Smart man, the spaceship takes off.
Okay. So we had our slope field from -2 to 2, and the good thing about this one is it doesn't just do whole numbers for x and y, of course. So it gets all these points in between what's called the integer lattice. Lattice points, whole number x, y coordinates. Okay. So we got that nice looking slope field. And then we could put in our, let's see what happens. What was it, 0, 1? So you can see there's some weird business here. Initial point, x equals 0, y equals 1.0. And you can show the solution through the initial point. I noticed just playing with this, it's had some problems with strange points if you run up against a vertical tangent, things like that. It's working hard. But I know it does.
I've never seen Excel like in pain.
Usually it's the other way around.
It feels really good, actually.
Yeah, it has to work harder than other things, that's for sure.
It's not optimized for heavy math, no.
No, not this high, I mean, like, just this many computations and things.
For adding.
There we go. Okay. Okay, so we ran up to some problems because it was like, oh gosh, it was supposed to be a 0 somewhere in here, but, you know, yeah, it does go off and,
Pretty close to equilibrium,
right.
Zero.
The other one we put on there was y1 equals -1. So x being 1 and y being -1. So you guys can play with this. This is this is the thing. This is you can save this as an Excel file. Just don't save the changes and you'll always have it in its, form that I found it. Just don't save it after you mess with it and you can always pull it up and put in a different equation. So we got a new one. -1 is the initial point right here. So it should go off and follow those little guideposts. Wow. The TI-89 is probably faster.
A little bit, yeah. Especially when Carly has it loaded onto this and it like runs at like actual computing speed.
Mm-hmm. There we go. Yeah, that's not so bad. So they put in these dots, which is interesting. You can see the rate of change because these dots are positioned equally distant horizontally. So they have the same horizontal distance between consecutive points. So when they're spaced out like this, that's just because of the slope of the curve at that point. They sort of thin out. It looks like it thins out. Okay. All right. So yeah, when you're doing homework, try and get, if you can open D-Field, that's a good one. It's easy to use. You can define a whole lot of different types of differential equations with it. You can also put in parameters. So it has some parameters that you can define and change the values of those. Yeah. Okay. All right. So D-Field, that's too bad. There is a way of doing this as well with Maple. And my intention with Maple is just to do some basic things in here, okay? And then you guys can play with it if you like. Now, to plot anything, you need to have the command with plots. And if you do a colon, it suppresses the output, so you don't see all the libraries that carry with it. And differential equations is DE tools. With DE tools. Okay. Now, if you can get the syntax for this is even nicer than the Excel. So I can define a differential equation as follows. If you want to make an assignment, colon equals, and the differential equation, DIFF, and don't worry about memorizing this. Yx and x. So a differential equation involving both y and x. You always have to give the dependent variable y as a function of x. So it needs the parentheses there. There we go. Bigger. All right. Come on, get to the other side of that. There we go. All right, and say our differential equation was just simply x minus 2y.
Does it matter that you have those capitalized in here?
Yes.
They're not supposed to.
It was not supposed to be in caps lock. X minus 2y. Okay, so that defines the differential equation and it gives you the output. Okay, it recognized that, that's a differential equation, there we go. And then to plot that, it's just like plotting a graph in 2 dimensions, because it is. Plot, and I've already assigned that differential equation just the value dE. So that's the plot structure. I just put that back in there. And then we're doing it y of x, and I give it a range. X from -3 to 3, y from -3 to 3. And it doesn't like it, of course. Plot dE plot, it expects its first argument to be the type blah, blah, blah. Okay. I hope that's not, there might be a signed word, signed value or something. No, not dE. Okay.
Maybe it's yx comma x.
What's that?
Don't you have to define both the independent variable and the dependent variable? Yx comma x like you did above, or not?
Right here?
Yeah.
Don't
X, you can.
think so, but let's see. Well, luckily I brought this with me, sorry. The big book, old maple. Okay, so we assigned that properly. Oh, of course, it's not just simple plot. It is not simple plot. We're doing D field, direction field. D field plot. Okay, and let's try and get rid of that. Okay. Now, why did you do it?
There's the field plot.
Oh, I spelled it wrong. F-I-E field. Okay, that's right?
Yeah.
Okay, there we go. All right, so here it is from -3 to 3 in both directions, and that generates it, of course, much quicker. Okay? All right. Let's work on an example, and I'm gonna use Maple for this after we isolate this, but so example, let's generate all right. So let's generate a direction field for the first order differential equation x y prime minus x equals y squared. Okay. And we'll do it over -2 to 2 on the x-axis by -2 to 2 on the y-axis. Okay. So notice that this equation is not in that nice form where it's just dy dx equals something. So we just need to do a little bit of algebra to extract that y prime. All right, so I could say that xy prime equals y squared plus x. X plus y squared. If we then divide both sides of that by x, same algebraic techniques as every other algebra class. You can isolate the y prime, or call it dy dx. X plus y squared over x, or 1 plus y squared over x. Notice x cannot equal 0. So there would be no solution to this if x is 0 and y is anything other than 0. Right? We have a false statement. So there's going to be some weird action near x equals 0. It's predicting that y prime, well, as x goes to 0, if y is non-zero, then that becomes infinite. So there's going to be some strange, some peculiar stuff near x equals 0, yeah? So should we do this with direction, the Excel? See how it does?
Sure.
Does it take a while? No. Let's do it. Let's use Maple. And I will put, this is what I'm going to do. When I post this up, I'm going to just put the commands here. Take a little time and put the commands. And I'll try, what I think I'm gonna do is keep a sort of running cumulative bits about Maple, okay? And I'll post that online, you can find it, so I'll put how you do direction fields, okay? And I'll put that under, well, where do I put it? Overheads and handouts, or the technology demos, in-class demos. All right, but let's use Maple on this. Now that we know what the command looks like, we're going to define the differential equation. You can call it whatever you want, as long as that word is not a reserved word, so the name of some command. Okay. All right. So we want it to look like 1 plus y squared over x. Divide by x. Okay, good. Now, the good thing is, I don't need I don't need to put that equation anywhere else in there. It's stored as DEQ, so I can just hit enter, and there it is. Okay, so there would be our direction field. Very weird business around x equals 0. Okay, although at 0, 0, it looks like it's defined. Okay, so yeah, you can prove that the solution. What's that?
Would it want to try and define it because of the one?
Now, it depends on how, in the original equation, if y, well not that one, but the original form of the equation, if y were the constant function 0, and x were 0, then you get a true statement. Okay, but for a point.
When we express this explicitly as right now.
Yeah, and I think that's called a singularity. All right. Now, I was kind of curious how this would do. So delete that, and let's just put 1 plus x squared.
Y squared over x.
Oh, it's y squared over x, yeah. Y squared divided by x. Uh-oh, what happened there? Delete from, say, -2 to -2, or -2 to 2.
So we start at this, you have to get into this one. Yeah. We just can't play it in this number.
I'm going to back this up.
I think Maple might be able to handle that for
Keep it in its pristine shape.
but essentially, yeah, we just want to answer it.
Okay. So I wanted that one to be 1
So we can't put that.
plus
That,
y
do
squared.
one, do
over
x on
x.
one side, right?
Let's just keep it at -3 to 3.
Do you want to take off the original point, or?
Well, this will just do the slope field alone.
It's moving pretty fast this time.
Yeah, it went faster in my office. I don't know why. You know, computers have little strange things about them. One might perform faster than the other. I was pretty impressed.
Kind of like Pac-Man.
Mm-hmm.
It still reminds me of somebody. That's the only thing I see.
All right, and so we're going to put in an initial condition as well.
Put in 0, 0.
Well, I might break it. I searched for the ones where I think there's a pretty good, well-defined curve, like 1, 0.
Break it.
All right, so x is 1, y is 0. Let's put that initial condition. See how long it takes to even just do that curve. Still working?
It ran into one of your undefined.
Oh, did it anyway. All right, I hit end. Yeah. So it has a problem when x approaches 0. And that's going to be a vertical tangent up here. Okay, so not bad, not bad. All right, let's look at one more example, and then we're gonna, then I do have an activity. And don't worry, you won't have to generate anything by hand. Okay. All right, so example, and an application or one model of population growth is the following. So if you, if P is the population at time t, then the rate of change of population over time. Okay. This one right here is called the law of natural growth. Okay, and if you read about it in the book, it's a very simple one. It says at any time, the rate of change of population with respect to time is proportional to the current population. So if you have a large population, you have a large rate of change, more people to procreate or whatever, more organisms, whatever they are. Whereas when P is very small, then there's not as many people to procreate, not as many individuals, and the rate of change would be small as well. So it says the rate of change is proportional to the current population. The larger the population is, the larger the rate of change. Okay. Now, and it's a very simple, you could look in the book and see the general solution for it. But this is a little bit more sophisticated model. Okay, so you build in this part, 1 minus Pm. Now, P over M. P of t represents the population at time t. Non-negative. And both K and M are positive constants. Okay. So a few observations. Okay, we want to read this equation and tell us a few things. So for instance, if P is less than M, think real hard. What kind of fraction would P over M be if P is smaller than M? Well, right, less than 1, right? It's a fraction. If P is less than M, then that's less than 1. And 1 minus that, 1 minus P over M would be positive, yeah? Because we're talking about 1 minus a fraction less than 1. All right, and K is positive, so I have a positive times a positive. That means that dP dt would be positive. And that means, what about the population? Mm-hmm. If the time rate of change is positive, that means the population is increasing. All right, if, we're just going to consider all the possibilities, if P is equal to M, then what can you tell me about that fraction P over M?
1.
That's equal to 1. And so 1 minus that is 0. All right, and if 0, and if I get a 0 out of that factor, then the rest of it is 0. That says dP dt equals 0, right? And what does that mean?
No growth.
Right, no growth. So population would be constant. No growth, increase or decrease. Now, the other possibility is that if P exceeds M, what kind of fraction would that be if P is larger than M? Right. P over M is greater than 1, which means 1 minus that is negative. And that implies what? That's negative and K is positive. We took that on assumption. If K is positive, that's negative, then our time rate of change is negative also. And what does that mean about the population? Population is decreasing. So that constant m does have some physical meaning. We could refer to it as when population is less than m, the population is increasing. When the population is greater than m, the population is decreasing. When p is exactly equal to m, that says it's level. There's neither an increase or decrease in population. So m can be referred to as the carrying capacity. Okay. All right, so further on in this example, let's keep it going. So let's take some specific values, okay? Because right now, k and m, they're constants. These are called parameters. We don't know their value, but we're taking k and m to be constants. So those are parameters in this differential equation. But let's say we take some specific values. So k to be 0.08, and we'll take m to be simply 1,000. Okay? Then our differential equation becomes dp dt equals 0.08 p times 1 minus p over 1,000. Okay? All right, so we're not going to generate that by hand or anything, but this is what the that's what the oops, right there. That's what it looks like. The slope field of it looks like. Okay. By the way, I don't think I mentioned it. That's called the differential equation is a form of the logistic model. Logistic growth. There it is. Okay. So yeah, this is just called the logistic model for growth. All right, so you don't see it with the popular types of growth like exponential or quadratic function. The solution to this, well, it's a pretty complicated type curve, okay? But we can easily, fairly easily, as long as the software is cooperating, generate a slope field for it, okay? So time here, whatever it is, hours, years. If you're talking about bacteria, maybe you're talking about hours, and a population, okay? So sketch the, we're just going to sketch the particular solution curve corresponding to each given initial condition. So if we know that at time 0, p of 0 is 100, where is that on the graph? How about right here, 0, 100. Then we can follow the direction field and generate a curve. Okay, so what will that look like? Well, about like that, and then it starts to increase. It's increasing the whole time. Increasing at an increasing rate, it looks like. And then what happens? Right, it looks like these things. Right, it looks like, and who knows, somewhere around there. It flattens out, doesn't it? So I'm going to mark these different colors corresponding to each curve. All right, now what if p of 0 equals 1,000 right on the nose? Yeah, look at this. If p of 0 is 1,000, if p is ever 1,000, 1,000 over 1,000 is 1, p over m is 1, 1 minus 1 is 0. And if you follow the, it looks like this is the 0.
Equilibrium.
That's an equilibrium solution. And on the other hand, finally, if P of 0 is 1400, then what do we got? Right, 1400 at time 0, right here. It looks like it's decreasing pretty fast. Oh no, same color. And it brings it back towards that equilibrium. Okay. All right. So the curves that we've drawn are called logistic curves. We don't know what the formula looks like of that curve because we didn't solve it. We did not solve it algebraically anyway. Okay. We got some nice curves that approximates the shape of it. But it's kind of interesting. It's always if the population starts off below that cap, that carrying capacity 1,000, then yeah, the population is always increasing. But it starts off increasing at a very high rate. So increasing at an increasing rate, and then it hits some point where, yeah, population's still growing, but leveling off. So increasing at a decreasing rate. The second derivative would be negative. So there's some inflection point somewhere in there. Whereas just a straight exponential function won't have an inflection point, e to the x or something like that. Okay. All right. So any questions? All right. Let's take about 15-20 minutes on this, and then we'll do break, because then it'll be a good transition point.